The Nobel Prize in Chemistry was awarded to 3 scientists for their contributions to the study of minuscule quantum dots. At one point, quantum dots were believed to be impossible to create, but now they are a prevalent component in various electronics such as computer monitors, LED lamps and TV screens. 3 scientists who played integral roles in the creation of these colorful nanocrystals are Mungi G. Bawendi, Louis E. Bruce and Alexei N. Ekimov. As recognition for their work, they have been awarded the 2023 Nobel Prize in Chemistry by the Royal Swedish Academy of Sciences. The Academy granted this award for the discovery and synthesis of quantum dots. This news had already been leaked to the Swedish media, an uncommon occurrence when Johan Akvist, the chair of the Academy's Nobel Committee for Chemistry, officially announced the news. During the announcement, he presented 5 flasks of quantum dots in various colors to visually aid the audience. Quantum dots are tiny semiconductor beads, measuring only a few tens of atoms in diameter. A pinhead could contain billions of them, and the smaller the dot, the more superior its electrical and optical properties due to quantum effects that come into play at such small scales. These dots emit a bright glow upon being illuminated, with the color of the light being determined by the size of the quantum dot. Larger dots produce red light, while smaller dots emit blue light, making it possible to customize quantum dots to specific light frequencies simply by altering their size. Since the 1930s, physicists have held the belief that particles at the nanoscale would exhibit unique behavior. This is due to the principles of quantum mechanics, which denote that there is limited space for electrons when particles are that small, and as a result electrons are squeezed so tightly together that the properties of the material can change drastically. In the 1970s, scientists were able to successfully create thin films at the nanoscale on top of bulk materials that had optical properties dependent on their size, as predicted earlier. However, it was widely believed that these films would have minimal practical use, as they required ultra-high vacuum conditions and temperatures approaching absolute zero to be produced. The ancient art of colored glassmaking yielded a solution. Glass artisans discovered that by adding silver, gold or cadmium to the molten glass and adjusting the temperature and cooling process, they could produce a wide array of hues. Later, scientists discovered that the colors were produced by minuscule particles embedded within the glass, and that the size of these particles determined the specific color that would be manifested. During the latter part of the 1970s, Ekimov, who had recently earned his PhD, launched an investigation into the optical traits of colored glass at the S.I. Vavilov State Optical Institute in the former Soviet Union. He utilized some of the optical diagnostic techniques he had employed in his doctoral research on semiconductors, utilizing light to illuminate the materials and gauging how it was assimilated to gather more information about the structure of the crystal. When Ekimov began the process of tinting his glassware with copper chloride, he embarked upon a journey of discovery. After cooling the glass, he utilized X-ray technology to examine his creation and found that small crystals of copper chloride had developed. He experimented with the temperature and heating time, varying them between 500 degrees to 700 degrees C and 1 to 96 hours, respectively. He discovered that the sizes of the crystals ranged from 2 nanometers to 30 nanometers, with the size being directly proportional to the temperature and heating time used. The particle size also impacted the way light was absorbed by the glass. Similar to thin films created in the 1970s, smaller particles of copper chloride absorbed more blue light. These were the first quantum dots that were intentionally produced within a laboratory setting. Regrettably, Ekimov's unveiling of his discovery in 1981 was printed in a journal exclusive to the Soviet Union, which meant that researchers in other parts of the world were unable to have access to it. This included Bruce, who, in 1983, disclosed his own findings of freely levitating nanoparticles within a solution that also revealed optical effects that varied depending on the size of the particle. During his tenure at Bell Laboratories, Bruce conducted experiments with cadmium sulfide nanoparticles due to their ability to harness light energy for chemical reactions. He observed that these particles' optical properties changed after being left on a laboratory bench for an extended period, which he attributed to their growth in size. Bruce compared the optical properties of cadmium sulfide nanoparticles, measuring 4.5 nanometers and 12.5 nanometers in diameter, discovering that the smaller particles absorbed more blue light. This held true in his subsequent experimentation with other types of nanoparticles. Ekimov, who once held the position of chief scientist at Nanocrystals Technology in New York, was caught sleeping when he received a call from the Academy. He expressed his pleasure at receiving the award after 4 decades of toil. Meanwhile, Bruce, who is currently a professor emeritus at Columbia University, was also sound asleep when his phone began ringing continuously. When he finally returned one of the calls, it turned out to be from a TV station in Miami keen to get his reaction to the win. According to Bruce, they were the first people to tell me. Bruce expressed his initial reaction as being one of contemplation, specifically about the other highly skilled scientists in his field who had not received recognition from the Nobel Prize. He emphasized that the discovery was a collaborative effort, with contributions from physics, chemistry, and materials science. While he considers it a great honor and validation of his long-term dedication to the subject, he acknowledges that there are many other diligent scientists worldwide who work equally hard in their respective fields. Ultimately, he feels fortunate to have been acknowledged for his work, but recognizes the importance of recognizing and celebrating the achievements of all scientists. During the late 1980s, Bawendi served as a postdoctoral researcher in Bruce's laboratory, where he was heavily involved in the ongoing efforts to address a significant deficiency in his mentor's previous breakthrough. The production methods previously employed inevitably led to the creation of nanoparticles with inconsistent and unpredictable properties, especially in regards to their size. This hindered the potential practical applications of quantum dots. Although Bruce had made some progress in advancing the process, the nanocrystals produced still fell short of the desired standard. In 1993, Bawendi discovered the key to regulating the dimensions of quantum dots. He achieved this by fluctuating the temperature during the manufacturing procedure. Firstly, he inserted different materials capable of creating cadmium selenide into a heated solvent, ensuring that the solvent around the needle used for the injections was saturated. This caused small cadmium selenide crystals to form instantly, but they would cease growing due to the injection cooling the solvent. Bawendi then increased the solvent temperature, causing the crystals to start growing once again. The longer the process continued, the larger the crystals grew, and the solvent ensured a smooth and uniform surface. Once a simple method for producing nearly perfect quantum dots had been established, these nanocrystals found their way into practical applications. Upon receiving a call from the Swedish Academy, a groggy Bawendi, now a member of MIT, initially doubted its authenticity, but eventually confirmed that he had been awarded a Nobel Prize. "It's truly an honor," he exclaimed, though uncertain of what would happen as he was scheduled to teach at 9 a.m. that day. Bawendi also expressed his admiration for his former mentor Bruce, stating that he was molded as a scientist under Bruce's tutelage. He strives to follow Bruce's mentorship style in his own interactions with his students. In a statement by American Chemical Society President Judith C. Jordan, it was emphasized that chemists constantly strive to create new and innovative structures and frameworks of atoms and molecules that are customized to provide specific qualities and functions. An excellent illustration of this is quantum dots, which demonstrate the ability to conceive of a phenomenon, synthesize and adjust particles, and manufacture them with precision. Additionally, the capacity of quantum dots to adjust in size allows them to release distinct wavelengths of light, making them useful in numerous applications such as lighting, bioimaging, and displays. Quantum dots offer a multitude of benefits in various applications. One such example is their use in television manufacturing, where they allow for precise color tuning, resulting in more accurate and wider ranges of hues. Additionally, they use less electricity compared to traditional methods. Quantum dots are also an alternative to organic dyes in fluorescence-based biosensors, allowing for more accurate tagging of reactive agents. They can even be incorporated into glass windows, essentially turning them into photovoltaic cells capable of harvesting small amounts of solar energy. In 2013, German physicists were able to build the experimental equivalent of Maxwell's demon using a pair of interacting quantum dots. Furthermore, in 2015, scientists created quantum p-dots from recycled urine and utilized them in bioimaging mouse cells. The potential future applications of quantum dots include their incorporation into flexible electronics, tiny sensors and solar cells, as well as their use in encrypted quantum communication systems. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.